from the Lab 3 of Physics 2212 circuits. Okay, so the purpose of this lab is to use the principles of energy conservation and current conservation to predict the behaviors of circuits containing resistors in series and parallel, using multimeters to measure the actual values of conventional current and potential differences in the circuits, and examine the behavior of ohmic resistors and capacitors. A preview of the results is that a DC and RC circuit were built, and the behavior of the ohmic resistor and capacitors were observed. The calculated value of potential difference was lower due to the resistance in the wires and ammeters, and the time to charge and discharge were timed, and the capacitor's discharge is slightly lower than it charges in terms of time. The main concepts that we need to know are the node rule, which is in an electrical circuit, the total current entering a node must equal the total current leaving it. The loop rule, which is the algebraic sum of all electrical potential differences around a closed loop in a circuit, is zero. Ohm's law, which is the electric current through a conductor between 2 points, is directly proportional to the voltage across 2 points. And these will be used in our RC and DC circuits. So what initial conditions do we have for our circuits? For our DC circuit, which is shown in the top left, two 1.5 volt batteries, one 47 ohm resistor, one 100 ohm resistor, and two ammeters. And for our RC circuit, which is the bottom right, we have a 10 ohm bulb, a 20 ohm bulb, a 1.5 volt battery. We have two of those, and a 1F capacitor. For our DC circuit, our experimental procedure, we assemble the circuit, we connect the batteries and record the ammeter readings, current 1 and current 2. We convert one of the ammeters to a voltmeter, and we measure the potential difference across the circuit elements, and we draw approximate graph of potential versus position. So our system is basically our circuit, or two 1.5 volt batteries, two resistors, and two ammeters, and our surroundings are everything outside of the circuit. And our results for the DC circuit, when we recorded the ammeter readings for current 1 and current 2, we got 13.1 milliamps for current 1 and 13.3 milliamps for current 2. When we converted one of the ammeters to a voltmeter, we got 14.18 milliamps and 0 volts for the second one. And then our potential difference across the 47 ohm resistor was 0.6 volts, and across the 100 ohm resistor was 1.22 volts, and across the whole battery was 1.94 volts. And that's basically our theoretical potential difference. And our total potential difference summed to 1.83 volts, and this was lower due to resistance in the wires and ammeters. And then our approximate graph of potential difference versus position kind of looks like that. And this is because larger resistors have larger potential drops across them. And so the sum of all potential differences around the loop equals zero, which confirms Kirchhoff's voltage law. When a voltmeter is attached in parallel, it adds a high resistance path to the circuit. Because its resistance is so large, negligible current flows through it, so the ammeter reading remains essentially unchanged. And for our RC circuit, we set up our RC circuit with the following components. We observe the behavior of the capacitor charging and then discharging, and we repeat the procedure using the other bulb. And we measured the charging and discharging times, and we used a video times. And so our system is basically our circuit, our RC circuit, and it's the 10 ohm bulb, the 20 ohm bulb, the two 1.5 volt batteries, and the 1F capacitor. And their surroundings are everything outside of the circuit. So how long did it take for the capacitor to charge? For the 10 ohm bulb, it took 8.7 seconds to charge and 9.6 seconds to discharge. And for the 20 ohm bulb, it took 36 seconds to charge and 45 seconds to discharge. And our sources of error that could have happened are you could use a phone timer. Since we used the phone timer, it wouldn't have precise readings, and our ammeter also could not have been precise, and our calculations around it. And these greatly affect our readings. So what if you charged a capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge, and would this prediction happen in real life? So if you charge a capacitor with no resistor in the circuit, it would target potential difference. It would hit the target potential difference instantaneously. However, this wouldn't really happen in a real environment, as no wires have zero resistance. And so it's going to be slightly less than the target potential difference.